Thanks for inviting me. Today I'm here to talk about 4D reconstruction with radiance fields, or really I was asked to discuss the applications of radiance fields, and so I'm going to talk about the latest work in my lab. Before we get started, as a way of introduction, um, my name is Angjoo Kanazawa, and my lab has been doing a lot of work in this area. And it's interesting to give you a little bit of a perspective. When I was making this, it was so interesting, because it's already been 5 years since Nerf. That's kind of surprising to me, actually. Um, in March 2020 was when the paper first came online. And so by this March, it's going to be 5 year anniversary. So a lot of things have moved, no wonder. And so it's, if you're not aware, perhaps when the Nerf came out, it was super slow. You couldn't even like move it around in a browser. And then today I have a couple of really cool demos that actually show you that you can see some of these things online on the website. And so that was one of the things that we did, was to make it be a full-time interactable viewer. And then, of course, it became faster training with panoxels. I'm sorry. Um, and panoxel was one of the earlier work, actually one of the earlier work that showed that no neural network was actually necessary, paving way towards representation like Gaussians, which also doesn't use any neural networks, so explicit representation. And then, of course, there's lots of application that expanded this to a larger scale data and generative models. And then in the summer, Gaussian Splats was released, and it's almost a year from then also. And so around this time, we basically wanted to decided to work on a single repository that put everything together. And perhaps this has been talked about, so I'm just going to mention it just as a timeline, really. So we released Nerf Studio in October 22, and uh, sorry, I don't know why, but here we go. Here we go. It just makes me easier to do this. Okay. Gaussian Spot in August 23. And so that's the kind of so this is one of the things that my lab develops. With lots of collaborators from online. And so I want to do a quick explanation that you may know of and has been discussed, but this is an end-to-end framework where you can take a picture, and all of the popular Nerf and Gaussian implementations are done in a modular way that you can combine with a WebTime viewer that you can export it to many different settings. So it's a lot more flexible for developers. And here's some cool VFX effects that my videos that one of the master's student who is now a PhD student doing research in HCI made. Um, and we are doing a lot of tools around this. And I want to mention Visor because it's actually quite important to be able to visualize these 3D results intuitively during developments, and also for results. And so Visor actually is not just for Gaussians or near radiance fields, but also for any other types of 3D inputs. And later I will show you a couple of exciting demos where you can people are actually using Visor to host interactive 3D results or 4D results online. So we're gonna do that. But this is really the tool that's part of Nerf Studio. And here's Justin. This was like a year and a half ago, I think, when we first got this ability to look at Nerf Studio online on the web, and he's doing it on the airplane. Of course, back then the backend was still not Gaussian, so it was like a little bit slower, but now it's very, very fast. Um, so thankfully, Nerf Studio has a lot of contributors, and so other quality of life updates are made constantly. So if you're interested, please join the community, and there's a lot of people on the Discord, and there's a lot of things you could do. So as a part of this open source effort, I went away one summer when the Gaussian Spot came back for like a month in Japan. And when I came back, I found my students implementing G-Spot, which is fantastic. Because the speed really at which you can render and do these things are really important. We actually wrote white paper where we actually did these evaluations as well. But I just want to give some of the latest updates, which allows you to do really large scale rendering. So if you actually go out, this is actually many rooms of the garden scene. And so also multi-use distributed training. And we were really lucky. I want to take an example and mention Jeffrey because he was just like a full-time person in the world, and then he got excited about this project, and he basically came and then implemented like 5 papers in GSplat in like a very short amount of time. And then now I think he's looking for PhD opportunities. So I think that's a really nice way in which the community has, really kept on adding to GSplat. And so there's many more features that has been added. I recently found out that some of the view in 3D is actually running on Nerf Studio using 3D Gaussians, which is really cool. Perhaps you are aware of these, Nerf-based approaches. They can also reconstruct the background appearance of the scene, but also change the time of the day. So this was like a paper that was in Nerf, but what's really exciting is that now that it's actually done in Gaussian, it's actually, you can do it at an interactable speed. Then this demo, it really feels like jumping into a photograph, And so that's another work that one of the undergrads who happened to be at Berkeley did, which is all there. Let's see. And also, of course, we recently had a paper in Nerf Excel, which was trying to really study how to scale Nerfs to very large scenes, and how to principally handle this. And Relon came up with a very nice solution. And so these are the developments. Okay. So let me get into some of the research or beyond 3D capture, because the things that I've shown so far are about doing novel view synthesis or 3D reconstruction. The really nice thing about NeRFs is that you can store anything in the field, in the neural radiance representation at large. However you implemented Gaussians or NeRFs or whatever, whenever you have a representation that is storing something in 3D by neural field or Gaussians approximating it, one nice thing is that you can actually store other features like clip features or other language foundation features. And so in this case, you can actually search the scene and do like, where is Waldo? I'm going to keep this talk quite high level, so I'm not going to get into the details of this. But this is really trained by simply letting another network that outputs clip features and then rendering it against the computed clip in 2D. Now there's a little bit more subtlety because this actually have to be done at multiple scales, which if you're interested, you can take the paper, look at the paper. But one thing I would like to emphasize is that really there's a lot of power that comes from putting these semantic outputs that comes from these data-driven priors into 3D space. So in clip, if you do this task of where is the lily, and then do sliding window, and look at the heat maps of sliding windows that gives you the highest activation in 2D, which is the center column, you see that it kind of fires around the lily, but it's really blurry. But once you actually do 3D reconstruction and do this in the process of reconstructing novel view synthesis of NeRF, and do it with our LeRF, you can see that the lily activation is a lot more sharp. And this is because the multi-view consolidation process really helps you identify, what is in the foreground, what is in the background. I mean, there's nothing in the air. And so you get much more crisp prediction. And, clip and these kind of features are not known to be not really well grounded in images because they're only trained on captions and images. But this is a very nice way to actually ground the predictions into what's in the scene. Anyway, so this is Justin and CMK, Changmin, who worked on this project. They went to Paris to present this work. They captured themselves in their studio. And the point is that inside, normally Nerf has no meaning, but we added meaning so that you can actually do these searches. And here is to demonstrate that these searches can be really wide open language and very long tail distributions thanks to these powerful models. Okay, so after this work, there's other type of semantic information other than language, which is that of grouping. It's like which objects should be grouped. Now we can name things, but if you think about it, um, the entire scene is stuck together. And it's not really something you can pick up, which is something that comes naturally. This is actually quite non-trivial. And that was what we looked into in this work that we presented at CVPR 2024. And one key about this is that a scene can be grouped in multiple ways. So you can group each individual keyboard, but you can also group the entire set of keyboard. And so there is this aspect of the grouping is really task specific. And segment anything somewhat punts this question because it just outputs a bunch of groups. It's like a bag of segments, and they don't necessarily have any consistencies throughout the scene or across the different views. And so again, we can consolidate this in 3D. And the key idea here was about this question of like, which ones should we group, was to use physical size of the conditioning to group in 3D. So for example, given this picture or a scene of watermelon, there are multiple ways to group this watermelon because you might just want the watermelon, but then you might actually want the whole slice of the watermelon, a bigger slice of it. And both of these are valid watermelon, and it really depends on what your goals are about doing what to do with the object, you know. And so to keep this flexibility, the idea is to give a scale conditioning that captures, a small thing or a big thing. So basically, intuitively, you're saying like, here, give me something that's big that I can move around. So this whole, tabletop is a big thing, then you can move the entire tabletop with stuff in it. But then if you say, I want small things, then you actually allow you to get this cup. So just to make it clear, the input is a scan of the scene using Nerve Studio or any other kinds of Radiance reconstructions. Oh, actually, sorry, just images. Just images. The input is just images, multi-view images of post images with a set of 2D sum masks, the bag of grouping that we have extracted away from these images. And the output is a 3D reconstruction as well as the multi-scale groups in 3D. And similarly to the clip case, here we're also going to train an extra feature. Instead of making this into clip or anything, now we're going to present this. This is a pairwise affinity feature, or like a feature that when you compute the distance, it should capture the right distance. So we're going to compute some features that this feature, if they are different, belong to different group at a specific scale, they should be really far away from each other. And if these points belong in the same group, then they should be very close to each other. So this idea of contrastive learning. There's more about the method, but I'm gonna focus on the results. And the nice thing about this approach is that it allows you to extract groups of different sizes. So for example, you can look at this, the bulldozer or tractor, and you can actually extract the whole thing, or just the shovel, or just the pieces. And break these things apart from the room, from the scan. And you can even make this interactive by, there's a continuous actually thresholding based on the scale. But we also can do automatic grouping on top of it. And then here are some of the results where the scene with the donut, you can actually cluster into different groups. And there's more, so there it's more coherent with that level of grouping. And then now it's starting to be all the boxes except some of those two boxes of the two donuts on the right side, happen to be clustered in the different things. So there can be more work into this, but really it's a nice way to actually group the object consistently in the scene. And here is some examples of more examples. So this is the smallest scale, and once you erase it, you can get the scale that corresponds to the thing that you would like to want. So there is a question of what should really be the level of scale. And perhaps it's a really interesting question to incorporate like motion to figure out what should really be a group. really need to have a video. But the nice thing about this is that it really essentially allows you to extract assets, especially if people can specify which scales they would like to do. And here is a very simple reel to sim. So here's a scene that we captured in my room, and we basically put it through it in Blender by putting a very simple mesh kind of underlying representation, and then doing some robots, because now we're really getting to more usable scene representations. So one thing is that with language and knowing where to grasp, you can actually tell your robot to grasp objects by specific locations, like saucepan by the lid. And this could be a nice way to tell them to assign like the language of like the nouns by the physical locations. And so that was a nice very cool demonstration. Um, but really, I would like to talk about 4D stuff. Okay, and so here, let me think about this. Here we go. Um, oops, I guess maybe you're hearing this, whatever. Okay. Okay. So this is work called Robot See, Robot Do, which is trying to make the robots imitate what is shown by humans, and we're going to do that by 4D reconstruction, which is we're shown in the middle. Okay, so I think this video really summarizes it well. So humans imitate by watching people, so we enable the robots to do the same. And here are steps. You scan the object. You show a monocular video of the desired motion. We process the 3D reconstructions into these latent representations and also Garfield parts. Now we can actually fit these objects to video, and which can be 3D coherent. And then you plan your robot action. Okay. So really the key innovation here, there's as far as the representation in 3D, 4D is considered, is really doing monocular 4D reconstruction, which is a very challenging problem. And by 4D, I mean 3D space and time. So 3D things that are moving in time. And so one caveat that made this problem easy is to actually assume that there is this Garfield scan of the object. Once you actually have that template and now parts, then you can parameterize the motion in a very low dimensional way, because if there's 4 parts, you really only need to solve for 4 different transformations in SC3. And then the idea is to reconstruct these parts from a monocular video, which is still very challenging, but it allows us to use a lot of the existing tools. Okay, so step 1 is to do reconstruction, and we call this as part 4D differentiable part models, because essentially that's what we're coming. So we scan the object, and then we also do optimized dyno, just like you could do clip features. Dyno is a self-supervised features that preserves a lot of correspondences, and so this is why we are using this, and you'll see why, because we need a way to actually set the correspondence between 3D and 2D. And then we run Garfield, and often what we had to do was to actually pick the smallest group level, because that's the most over segmenting is the best way than under segmenting it and grouping 2 things that move differently together. So once you get this grouping, we're going to fit this to video. So here are this. So you can think of this as template models. If you're familiar with 3D human motion reconstructions, there are models like simple body model, which is a statistical body of human motion, human body that you can use to manipulate. So you can think of this as a puppet. Now we have a part-based puppet of any object that you have scanned. And each of these parts now have, local transformations. Now, all you really want to do is to optimize this part location such that it minimizes the dyno image that is computed from the frames in the form of analysis by synthesis. Basically, you're asking solve for the optimization that gives you the observation. Okay, so here are some of the results. And actually, I don't have slides for this, but this is actually a caveat. It's a very challenging problem. Even if you have the 3D shape, monocular videos, depending on the viewpoint, is just not going to give you that much information. So then you need to do a lot of regularizations on the deformations or on the transformation, like smoothness or as rigid as possible. And but in the robot interaction, it's reasonable because it's very reasonable that you can actually get to see the object, and the human is going to demonstrate it in a way that is, where the motion is pretty visible, or it's an active kind of interaction setting. Anyway, but here are some results of the 4D reconstruction, which is actually really cool. And this is I like this one a lot. So there's actually a ball inside that actually comes apart. And so really the innovation is that this is very similar to the kind of things we do in 3D humans, but there you actually have this data-driven 2D to 3D correspondence. You know, like what is wrist? It's very, very robust, foundation models like VID pose that can say this is head, this is leg, and this is stuff. We don't have any of that here. We're actually doing all of it with Dino, which is, good, but it's not perfect. But then this known 3D template really helps you kind of resolve the ambiguity to a degree and actually get these kind of results. Okay, of course, once you have this, then you do your robot trajectory optimization so that this type of the motion that is exhibited on the part is reconstructed as well. And this part I'm really not going to talk about. I mean, you can, read the paper. But here are some results on Real Robot. And the nice thing about this work is that you're really looking at the object motion. So it doesn't really matter relative object motion. So it doesn't really matter whether the object is in certain directions. It doesn't actually have to object doesn't have to be in the configuration that it was shown to you. Because it's really like what is the relative impact. Um So, I guess should I do this here? Um, Maybe I will go back and do it later. Oh, well, yeah, here are some more results. Okay, yeah. Let me see. Let's just go to the interactive results. So, this is the really exciting thing about Visor and my students who are really passionate about having cool really making 3D accessible, which really requires you to really see it in 3D. So if you can see my screen, I hope it's not too laggy with Zoom, but you can try it out. You can actually go on the website, and this is the reconstruction. Now, this is really, okay, later I'm going to show you more. There's one more that I think really blows my mind because I just did not think we could do this kind of thing like even 2 years ago, even when the Nerf stuff was around, because it's very slow usually, right? I mean, like 3D is one thing, it's actually moving over time. The Gaussians really come in handy for this. So all of these are done using Gaussians, and it would not be possible without it. Really, that level of like, in order to get to 40, it really has to be efficient. And now that we have that, that's a really exciting development. Okay, so that is Lurf. And let me go here, which is that, we saw some good results, but it is still very hard. The 40 is clearly not solved. I just don't want to give an impression that this is solved. We picked nice videos where the motion is very clear, but sometimes the motion isn't very clear. So let's see. I mean, I think there's more significant failure cases, more this, but you see how like the tongue gets kind of twisted on the left side because the view doesn't really give you a lot of information, but having a good view will give you the right information. So this is something really to tackle, and we're still working on this actually as we speak to develop it. But I want to show you another work that actually does 4D reconstruction of anything and everything in the scene. And that is really this will work. So the idea is that from a video, you want to extract the camera, the scene geometry, and the 3D scene motion of the entire thing. And so general 4D reconstruction from videos, and this is a work called Shape of Motion, which is on archive. And really the idea is to take any kind of casual video and then enable it to do novel view synthesis, as well as not just the pixels, but also recovering the underlying correspondence across the scene. And I am super excited because there's a really cool interactive video demo. Okay, I will just do this. I'm gonna come back. Okay, I was just gonna do this. Let's just do it. Okay. And this is super exciting. I really didn't think this was possible. So let's see. Let's go to the interactive gallery. And I had a baby in February. And so this is my baby on her in a park. So if you do track length 0, then you can see the results. Now, okay, this isn't perfect yet. Okay, first of all, this also depends on very good initial camera prediction, which is using Megasum, which is one of the latest work that incorporates data-driven prior. So that's really key. But our approach allows you to densify everything and get these consistent tracks that understand the motion. Now, if you look directly from the side, it's kind of it's a little bit more circular than it has to be. So there's more, work to be done here. But I mean, these are videos that we captured. Like when we captured this, we're like, oh my God, this is like way too hard. You're not gonna be able to do this. This cat. Like the thing that you have to notice that the input is a single video and it's not really even moving that much, and we're really like consolidating a lot of the information here. And I think this is just super, super cool. The fact that you can even move around, this is just like, I don't know. I mean, things are really working in this area. And okay, all right. I think with the Zoom sharing, my GPUs are getting tired on my laptop. And so I really encourage everyone to just try. Some of these are super fun results. Like these are really monocular and yeah, it's very exciting. So please check this out. Actually, we just did an update to this shape of motion and with Megasum release. We haven't really tweeted about this. I was about to kind of like promote that there's a new cooler work because we improved it with the Megasum output. And so anyway. Yeah, so of course, when you look from the top, there are parts of the scene that has not been completely observed, and you would like to use some generative approaches to do that. And we also have some kind of directions that way. But let's see. Let me just tell you briefly how this is being done. And the idea really is to represent the entire scene of Gaussians. Gaussians that actually move persistently in the scene. So there's one Gaussian, and then you're actually moving them around, and that motion is actually the representation of the entire scene. So it's a persistent representation, just like in physical reality. And instead of doing this per Gaussians, we actually have a regularization because the 3D motion is low dimensional. We actually do this have a low dimensional basis on the motion representation. And this is a small key because like this is something like this using low dimensional way to do shape is always done. Like in humans, humans are low dimensional. We're not all like sets of points that move around. So then you actually do this low dimensional prior, but you did it on the category, like on the shape. Here we're doing it over time, which enables the shape to represent anything and everything in the scene, which enables you to do these category-free reconstructions. But of course, this is highly under constrained problem. So we're going to use depth maps, code tracker results like long range 2D tracks. I'm formulating this as an objective in our this is like the input. And so our approach is actually able to improve upon this. Basically, we get all of these like, semi 2D, 3D, 2.3D, 2.5D inputs. and we're going to optimize this underlying representation that's low dimensional so that it reconstructs it. I really think this is just like a bundle adjustment optimization for 4D, and so that's what it is. And then it allows you to get much more better reconstruction. Not only that, really, it preserves the correspondences, and so that's really the cool part. And this correspondence is actually improved upon. The thing on the left is like the input correspondences, which there's problems because it's done in 2D. But if you actually consolidate in 3D, it's much better. Okay, so anyway, this is where the projects are. And so please, I think you should just go over there and then look at the results. Now, I think I am starting to be out of time, but there's really, in this direction, there's a really cool paper that Genshan Yang led, who's at World Labs right now. And in this one, we like not only captured the cat in a room using these, Gaussians and like all these technology, but once we got the reconstructions, we actually learned a behavior model of how likely is a cat going to move. Okay, so here, this is Genshan's cat called Pikachu. He collected lots of pictures, videos of this cat in the same room for a month, along with a single reconstruction of the room. And then he reconstructed the whole thing. And now we also, on top of it, learn a diffusion model of like what the cat is likely going to do given some inputs like other people or goals, like so and that you can specify, or the agent can also explore its own goals and explore the scene. And so we basically have this cat simulator, and I think that's super cool direction. Really, it's really more like, once you get 4D, you can build these models of the world in a way that you can actually, control them. And of course, you may have seen these editing results, which incorporates generative priors. This is on a different note. This is like using generative priors and merging them into your 3D reconstruction to kind of like fill the missing holes that, I was just pointing out. And so that's kind of an exciting direction. And I also want to note this cool paper that my students worked on, which is trying to reconstruct cartoons. And cartoons themselves are actually not geometrically consistent. So you have to do some explaining a way to do. Anyway, I think I'm running out of time. And so I just want to thank my students without whom this is not possible. And here.